Analyzing ellipsometric data can be hard, especially for new users. This video demonstrates how the new FilmSense Model Builder feature automates the process of building and testing analysis models over a wide range of thin film applications. For the first example, we will analyze ellipsometric data acquired on a transparent alumina film deposited on a silicon substrate. Click the Builder button to switch to the Model Builder screen. Model Builder is self-documenting. Hover the mouse to see detailed descriptions of the various settings. First, select the substrate type as silicon, and we will use the default value of 2 nanometers for the native oxide. Next, select the film type as transparent and specify the starting material as alumina. And finally, we will use the default film thickness range of 5 to 500 nanometers. Now we are ready for Model Builder to do its magic. Click the Build and Test Models button, and Model Builder suggests that the fit is good, which means that the fit diff is acceptably low, and the best fit model is an ideal Cauchy model. The model results are shown in the table, with the simplest model at the top, followed by models of increasing complexity. Click the Parm Errors button to verify that the ellipsometric data provides acceptable sensitivity to the fit parameters in the selected model. Model Builder uses a combination of the tabulated fit diff and thickness error values when selecting the best model. For example, the more complex Cauchy with roughness plus grade model has a lower fit diff compared to the best model, but its thickness error bar is much larger. Click the Show Selected Model to see how the model was constructed. Here is the more complex model with roughness and grading, and here is the ideal model using book value optical constants and fitting only for the film thickness. Going back to the best model, model convergence over the full thickness range can be tested by clicking on the Validate button. If successful, the model can be saved and used for other similar samples, which completes the model building and testing process. For our next example, we will use a titanium dioxide on BK7 glass sample. Start by selecting a glass substrate with a glass type of BK7, and since the substrate was thin, the backside reflection box should be checked. The film is transparent and the starting material is titanium dioxide. We will use the default thickness range of 5 to 500 nanometers and then build and test models. In this case, the best model is a Cauchy with roughness and grading. Note that the simple book value optical constant model, the ideal Cauchy model, and the Cauchy with roughness model do not fit the data acceptably, as their fit diff values are more than 10 times larger than the best model. The more complex Cauchy with roughness model and grading is really required in this case, and it also fits the data better than models which included absorption in the film. In spite of its complexity, the best model still exhibited acceptably low error bars on all the fit parameters and good model fit convergence over the full thickness range. Next, we will analyze an ITO on glass sample, which is a very common transparent conducting oxide. For this sample, we need to change the glass type to soda lime, and we will select the ITO film type. Then build and test models. And for this sample, the best model used a Drude-Lorentz oscillator layer fitting for even more parameters. As is typical, the model using book value ITO optical constants provided a very poor fit. A Drude-Lorentz model fitting for 3 parameters provided a fairly good fit, but fitting for even more parameters provided the best fit. Oscillator models are a very powerful method for analyzing ellipsometric data, and Model Builder handles all the tricky details of setting up good starting values for all the oscillator parameters. We can plot the N and K values of the ITO film, and we see that rising K values at the longer wavelengths are due to free electron absorption in the film, which is accounted for by a Drudel oscillator, and absorption at the shorter wavelengths is accounted for by the Lorentz oscillator. Even with fitting for all the Drudel-Lorentz oscillator parameters, acceptable error bars are observed. Also note that the Drudel parameters can be used to calculate the film resistivity and sheet resistance values, which often correlate well with electrical resistivity measurements. Amorphous silicon films provide another good example of using oscillators in the ellipsometric data analysis model. For this sample, the substrate parameters are correct, but I will need to change the film type to amorphous silicon and also increase the film thickness range to 600 nanometers for this sample. Then we'll build and test models, and the best model uses a Tauch-Lorentz oscillator. Once again, the book value optical constants do not fit the data very well, but note that Model Builder automatically adds a native oxide layer on top of the amorphous silicon film. We can plot the optical constants of the Tauch-Lorentz layer and compare them with book value amorphous silicon. The general shape of the N and K curves are similar, but significant offsets are observed. This is due to differences in the film deposition method and process parameters, and such variations are very common for thin film applications. Next, we will consider a metallic film, titanium nitride on silicon. We will go back to a silicon substrate, and this film was deposited on a high-quality wafer that only had 1.5 nanometers of native oxide. We will select a film type of titanium nitride and limit the maximum thickness to 50 nanometers. The fit is good with a Drudel-Lorentz model that fits for more parameters. Looking at the N and K curves, we see large K values with increasing longer wavelengths due to the free electron absorption, which correlates with the high conductivity of the metallic film. As was the case with the ITO film, the Drudel parameters can be used to calculate the film resistivity and sheet resistance of the metallic titanium nitride film. Model Builder can also analyze automated mapping data. This provides a good opportunity to demonstrate the multi-sample analysis capability, which combines data measured at multiple locations across the sample in the analysis. By default, Model Builder selects data in the middle, left, right, top, and bottom of the sample. We will select a transparent film type with a starting index of 1.5 and a maximum film thickness of 600 nanometers. Then build and test, and an ideal Cauchy model provides a good fit to the data. Note the multiple sets of ellipsometric data shown in the plot, which correspond to different film thicknesses across the sample. The optical constant parameters are assumed to be the same at each measurement location. Including multiple ellipsometric data sets improves the accuracy of the determined optical constants, which is especially helpful when characterizing absorbing films, and Model Builder can help automate this powerful analysis. Model Builder can also be used to analyze dynamic in situ data that is acquired versus time. For this example, we will use an aluminum oxide film that was deposited by ALD. We start by showing the model and displaying the Model Builder screen. Then use the zoom bar to select the dynamic data range from just before the deposition was started to just after the deposition ends. Specify the substrate, and pseudo is typically used for in situ applications, the film type, which is transparent in this case, with a starting index value of 1.6. The nominal film thickness after deposition is 10 nanometers for this sample. Then build and test models. Model Builder suggests that the fit is good using an ideal Cauchy model. To determine the best model for in-situ data acquired over the entire deposition run, Model Builder automatically sets up a multi-sample analysis, selecting 10 data sets evenly spaced across the deposition time. The 10 thicknesses in the model correspond to each selected time, assuming that the film optical constant parameters are the same throughout the deposition. Clicking the Reanalyze Dying Data button fixes the optical constant parameters determined from the multi-sample analysis and fits the film thickness versus time. The model can then be saved to provide real-time thickness data for subsequent deposition runs. As you have seen, Model Builder can automate the ellipsometric data analysis process for most common thin film samples, and FilmSense is continually evolving Model Builder to support even more types of thin film applications.